This is the first recording of the Module 10 lecture. And in this lecture, we'll talk about the different chi-square tests. Right, the learning objectives for this module is that by the end, you should know how to find chi-square values using table 6. So we're going to learn a new distribution and use a new table of probabilities. You should be able to perform a goodness of fit test following the 5-step procedure that we learned in Module 9 and back in Module 8, and explain the decision of the test. You also should be able to distinguish between a test of independence and a test for homogeneity. And once you make that distinction, you should be able to perform a test for independence or homogeneity following the 5-step process and explain the decision of the test. And that explanation of the test is going to depend whether you're performing an independence test or a homogeneity test. Also, you should be able to perform a hypothesis test of a single variance following the 5-step process and explain the decision of the test. And finally, you should be able to calculate the confidence interval for a population variance or standard deviation and interpret the confidence interval. So that's what we intend to learn in this module. All right, the chi-square tests, I put this chart so that helps you to see how the chi-square tests are classified by the variable type. So if you're dealing with a discrete variable, then you will either be performing a goodness of fit test. This is when you're looking at a single distribution, or you may be looking at a test of independence or homogeneity. And this here you have more than one variable. Now, if the variable type is continuous, then the chi-square distribution is used to make inferences about a single population variance, either testing a hypothesis or constructing a confidence interval. So we're going to discuss first the discrete types. We're going to start with the goodness of fit test. Once we learn to do that, then we're going to learn to first distinguish between independence and homogeneity tests, and then perform each of these tests. And then at the end of this module, we'll then deal with a continuous variable, and we'll learn to test a hypothesis about a population variance and construct a confidence interval for a single population variance. All right, so let's talk about the goodness of fit test. This is covered in sections 11.1 and 11.2 of your test. And I should be clear that this is one of the many goodness of fit tests. So this is one of the possible tests that you can have. When we talk about chapter 13, we'll talk about the goodness of fit test of a linear model to the data. So here we're talking about the goodness of fit test for a multinomial distribution, and we'll see what that is. All right, let's start with an example. So a plant geneticist raises 250 independent progeny, and that means offsprings of a plant itself, under identical conditions from a cross that is hypothesized to result in a ratio of 9:3 to 3:1 of amber-flowered, orange-flowered, yellow-flowered, and green-flowered marigold plants. So this particular cross that was performed is supposed to produce plants with flowers of these colors in this ratio. Now, that's what the geneticist thinks is going to get from this cross. Now, that when they performed the experiment with 250 plants, they obtained the following frequencies. So 152 plants had an amber flower, and 39 of them have an orange flower, and 53 had yellow flowers, and only 6 of them had green flowers. So the question is, or our goal here is to test the hypothesis that the population of proportions of colors is a 9:3 to 3:1 at a significance level of 0.05. So this is an example of a goodness of fit test, where we want to see if we match these frequencies or these proportions given the observed proportions. So in this experiment, you can see that the flowers are raised and I should say plants are raised in an identical manner. There are 4 possible outcomes. Since the marigold plants may have amber, orange, yellow, or green flowers, the probability that a plant can produce any one of those 4 flower colors is the same for all plants. These plants are raised independently of each other. And since these plants can only produce these 4 colors, then the sum of the probabilities for each of the colors must be equal to 1. All right, these characteristics, if you think about it, they resemble the characteristics of a binomial experiment. And in fact, a multinomial experiment is like a binomial experiment. And in fact, the binomial experiment is a special case of a multinomial experiment. The difference with the multinomial experiment is that you have more than 2 outcomes. Or we say you could have up to k outcomes, where k must be bigger than 2. And the characteristics of the multinomial experiment are that they consist of n identical trials. Each trial results in one of k possible outcomes. Sometimes in these problems are called categories. And the probabilities of the outcomes, the pi sub I, are constant for each trial, where pi sub I, the subindex I goes from 1 all the way to k, because there are k probabilities of success, because there are k possible outcomes. And all these trials are independent, and the sum of the k probabilities is equal to 1. So if you look at the description of the experiment of the marigold flowers, well, we have exactly a multinomial experiment. So with a multinomial experiment, and that's what I'm explaining in this slide, in the experiment of raising the marigold plants, the geneticist assumes that the ratio of plants with amber, orange, yellow, and green flowers is at this ratio of 9 to 3 to 3 to 1. So to determine the probabilities, then we sum these numbers, 9 plus 3 plus 3 plus 1, and you see that is 16. And we then divide 9 by 16, 3 by 16, 3 by 16, and 1 by 16. And so that those probabilities sum to 1. So the null hypothesis for this experiment, or this multinomial experiment, is that the probability of success of each color, or more specifically, for the amber color is 9 sixteenths, for the orange color is 3 sixteenths, for the yellow color is 3 sixteenths, and for the green color is 1 16. And now we want to use the observed counts of each color to determine if this null hypothesis is correct. And that's what we're going to learn to do with this goodness of fit test. All right, so we're going to, as we learn in modules 8 and 9, here we're going to use this hypothesis test process. So as you already saw, how we state the null hypothesis is different for these kind of problems. And you will see that the direction of the test for these, the goodness of fit tests, there are always right tail tests. The distribution to use is different. It's going to be the chi-square distribution. The definition of the test statistic will be different. But then finding the p-value or the critical value, we'll do it exactly like we did with the t-test. But now we're going to use the chi-square distribution, but it's very similar to that. And then making the decision whether to reject the null hypothesis, we follow the exact same procedure. So if the test statistic falls in the rejection region, we reject the null hypothesis. If the p-value calculated from the value of the test statistic is smaller than the rejection region, then we reject the null hypothesis. So we follow this procedure with some changes. And the first change in the goodness of fit test is now we're dealing with a multinomial experiment, and so the null and alternative hypotheses are stated. The null, the probabilities have certain values. This pi sub 0, 1, pi sub 0, 2, pi sub 0, k, those are the assumed values of the probabilities, like in the case of the geneticist. We had the 916, the 316, the 316, and 116. Well, those are the hypothesized values of each of the probabilities of success. An alternative hypothesis is that at least one probability does not match the hypothesized value. And again, the condition is that the sum of these probabilities must be 1. If they are not summed to 1, you do not have a multinomial experiment, and then your test is not valid. Now, one very good thing to remember is the goodness of fit test is always right-tailed test. So we have only one direction for the test, right-tailed test. So that simplifies things. All right, so the distribution to use if the observed frequencies come from a multinomial experiment, and if the expected frequencies are, each expected frequency is at least 5 for each of the categories, then we will use a chi-square distribution with degrees of freedom equals to k minus 1. So in the next recording, we're going to see what this chi-square distribution is, and we're going to learn to use table 6 to find the chi-square values for a given degrees of freedom and for a given probability. So then we'll stop here, and in the next recording we'll continue with the chi-square distribution.